Imagine, for a moment, that you are standing outside on a clear night. The city lights have fallen far behind you, and the sky above is vast and unbroken, a deep, black ocean scattered with light. You tilt your head back, and the stars seem closer than usual, as though the atmosphere itself has thinned, as though the boundary between you and everything else has quietly dissolved. You breathe in the cool air, and you feel it, the particular stillness that only comes when you truly look up. Somewhere out there, beyond everything you can see, beyond every planet, beyond every moon, beyond the outermost reaches of the sun's protective embrace, two small machines are still moving. They have been moving for nearly 50 years. And they are not coming back. Their names are Voyager 1 and Voyager 2. They were built by human hands in the 1970s, assembled in clean rooms in California, tested and calibrated and packed with instruments by engineers who were young then, many of whom have now grown old in the years since launch. They were designed to visit the giant planets of our solar system, Jupiter, Saturn, Uranus, Neptune, and to send back what they found. They accomplished all of that and more. And then, their planetary missions complete, they simply kept going. They are still going now. Voyager 1 is the farthest human-made object from Earth that has ever existed. Let that settle over you for a moment, the way a warm blanket settles over tired shoulders. Of every object that human civilization has ever launched into space, every rocket, every satellite, every probe, every capsule, Voyager 1 has traveled the greatest distance from the world that made it. It has crossed a threshold that no object of human origin had ever crossed before, and it continues to push that boundary further with every passing second. It can be difficult, lying here in the quiet, to truly feel the scale of what that means. So let your mind drift outward gradually, the way your breath is drifting now. Slow and easy, and without hurry. Picture the Earth first. A blue marble, spinning gently, wrapped in its thin veil of air. The moon hanging nearby, a pale companion. The distance between the Earth and the moon is roughly 384,000 kilometers. A number that sounds enormous until you realize that it is, in cosmic terms, barely a step. Now drift further. The sun sits at the center of everything, and the distance from the Earth to the sun, about 150 million kilometers, is the unit astronomers use as a baseline for measuring the solar system. They call it 1 astronomical unit. 1 AU. Jupiter, the first of the giant planets, sits roughly 5 of those units from the sun. Saturn, draped in its rings, sits at about 10. Uranus at 19. Neptune, cold and blue and distant, at 30. And Voyager 1? As you rest here tonight, Voyager 1 is more than 160 astronomical units from the sun. More than 160 times the distance from the Earth to the sun. It has sailed past all the planets, past the distant scattered debris of the outer solar system, and out into a region of space that existed only in theory for most of human history. Both Voyager 1 and Voyager 2 launched in the summer of 1977, within weeks of each other, from Cape Canaveral in Florida. The year was one of enormous cultural energy. Personal computers were just beginning to appear. The first Star Wars film had just reached cinemas. And quietly, in the background of all of it, 2 spacecraft were being prepared to do something no machine had done before. They were twin probes, built to the same design, carrying similar instrument packages, sharing a common purpose: to venture outward and report back. And yet from the very beginning, they were destined to travel different roads. Their trajectories were not identical. They could not be, given what was being asked of them. Voyager 2 launched first, on the 20th of August, 1977, sent along a slower path that would carry it to 4 planets rather than 2. Voyager 1 launched 16 days later, on the 5th of September, on a faster, more direct route aimed at Jupiter and then Saturn. Despite launching second, Voyager 1 would eventually overtake its twin and claim the title of farthest traveler. 2 probes, 2 paths, 1 extraordinary mission. The key to their success, the elegant piece of physics that made the whole journey possible, was something called a gravity assist. You might also hear it called a gravitational slingshot, and the name is apartment. When a spacecraft passes close to a large planet, the planet's gravity pulls it inward, accelerating it. If the geometry of the encounter is just right, the spacecraft swings around the planet and is flung forward, gaining speed without burning a single drop of fuel. It is, in a sense, borrowing energy from the planet itself, and the planet, being so incomprehensibly massive, barely notices. The engineers and mathematicians who planned the Voyager missions used this technique with extraordinary precision. They had identified a rare alignment of the outer planets, an alignment that occurs only once every 175 years or so, that would allow a spacecraft to visit Jupiter, Saturn, Uranus, and Neptune in a single continuous journey, each planet's gravity pulling the craft onward to the next. This alignment would not recur in any of their lifetimes. They knew that. They launched anyway. Let that image rest in your mind as you breathe. The patience of it, the foresight, people who would never see the final results, planning a journey that would outlast their own working years, because they believed the knowledge was worth having. There is one more thing about these two spacecraft that makes them unlike any other object humanity has ever placed in the universe. Before they were sealed and prepared for launch, a small team led by the astronomer Carl Sagan was given a task: to create something that might speak for humanity, in case the probes were ever found. Not by another human. That chance is essentially zero, given the distances and timescales involved. But by someone or something else. What they created is called the Golden Record. Each Voyager carries one. It is a 12-inch gold-plated copper disc, fitted into an aluminium protective cover, engraved with instructions for how to play it. On it are sounds and images selected to represent life on Earth. Music from dozens of cultures, spoken greetings in 55 languages, the sounds of rain and wind and surf and thunder, the call of a humpback whale, the cry of a newborn baby. There are photographs encoded on the record. A mother nursing a child, a forest, a sunset, the chemical structure of DNA. There are mathematical diagrams, designed to communicate in the universal language of number and ratio. It is, in its quiet way, one of the most profound things our species has ever made. Not a weapon, not a monument to power, not a declaration of ownership. Just a message. Just a hand extended into the dark. As you settle deeper into rest now, let that image stay with you. Two small machines, carrying a golden record, drifting outward through the silence. They are not waiting to arrive anywhere. There is no destination. Their trajectories carry them outward along curves that will never loop back, never return, never bring them home. They are leaving, slowly, steadily, irrevocably, the way that sleep leaves the restless mind, gently, without announcement, until suddenly the distance is so great that the starting point has become something you can only remember. The sun, from where Voyager 1 now travels, appears as nothing more than the brightest star in a field of stars. Bright, yes, unmistakably bright, but no longer a sky-filling warmth. Just a point of fierce light in the endless dark. And still they move. Tonight, as you close your eyes and let the weight of the day dissolve, Voyager 1 is traveling at roughly 17 kilometers per second. Voyager 2 at about 15. They do not slow. There is almost nothing in the space they now travel to slow them. No air, no friction, no resistance. Just the faint, fading pull of the sun growing weaker with every passing moment. They will travel through the void for millions of years. Long after the Earth has changed beyond recognition. Long after our cities and languages, and every record of our existence has been worn away by time. These two machines will still be drifting, silent, patient, enduring, through the space between the stars. They are the longest-lived ambassadors our civilization has ever sent anywhere. They are older than most of the people listening to this. They have been moving, without pause, for nearly 5 decades. And they have so much further still to go. For now, let that vastness hold you. Let the idea of those two small probes, out there, right now, in the absolute dark, be something that gentles you rather than overwhelms you. There is something deeply calming about the thought that out beyond all the noise and brightness of the world, two quiet machines are sailing through a silence more complete than anything we will ever know. You don't need to go anywhere tonight. You are already exactly where you need to be. Close your eyes. The journey has already begun. There are moments in history that only exist because of patience. Not the patience of waiting for something to arrive, but the deeper, quieter patience of watching and calculating and understanding that the universe operates on its own schedule, and that sometimes the only thing a human being can do is be ready when the window opens. The window that made the Voyager missions possible opened in 1977. It had been centuries in the making, and it would not open again for another 175 years. As you rest here now, let your body grow a little heavier with each breath. Let the muscles in your shoulders release. Let the thoughts of the day drift to the edges of your awareness, like distant lights seen through a fogged window. There is nothing that needs your attention tonight. There is only this, the slow, remarkable story of two spacecraft, and the extraordinary moment in time that allowed them to exist at all. To understand what made 1977 so significant, it helps to think about the outer solar system as a slowly turning machine. The giant planets, Jupiter, Saturn, Uranus, Neptune, are not fixed in place. They are orbiting the Sun, each on its own path, each moving at its own speed. Jupiter, the closest of the four, completes one orbit roughly every 12 years. Saturn takes about 29. Uranus takes 84. Neptune, the most distant, takes approximately 165 years to complete a single journey around the Sun. Because they are all moving at different speeds, the positions of these four planets relative to one another are constantly changing. Most of the time, they are scattered across the solar system in arrangements that make a grand tour by spacecraft impractical. The distances between them too great, the angles too awkward, the journey too fuel-hungry to be achievable with the technology of the time. But occasionally, very occasionally, the planets arrange themselves into a configuration that changes everything. Imagine, as your breathing deepens and slows, that you are watching the solar system from far above. You can see all four giant planets at once, small points of light arranged around the golden glow of the Sun. Most of the time, they are spread out, distant from one another, requiring a spacecraft to travel enormous extra distances to reach each one in turn. But once in a very long while, the slow turning of their orbits brings them into a sweeping arc, a curved line of worlds, positioned so that a spacecraft launched at exactly the right angle can visit each planet in sequence, using the gravity of each one to fling it onward to the next. That alignment, that rare, patient, 175-year alignment, was in place in 1977. The man who first recognized the full potential of this opportunity was a young aerospace engineer named Gary Flandreau. In 1965, while working at NASA's Jet Propulsion Laboratory as a graduate student, Flandreau was assigned the task of looking for efficient trajectories to the outer planets. He began calculating, plotting the positions of Jupiter, Saturn, Uranus, and Neptune across the coming decades. And there it was. In the late 1970s, the four giant planets would swing into a configuration that had not existed since the presidency of Thomas Jefferson. A spacecraft launched during a specific narrow window could visit all four in a single continuous mission, carried from planet to planet not by brute fuel expenditure, but by the elegant physics of gravity itself. Flandreau recognized immediately what he was looking at. He called it the Grand Tour. The calculations were complex, the logistics formidable, and the funding never quite materialized for the full Grand Tour vision as originally conceived. But the core idea survived, and it became the foundation of what would eventually be called the Voyager program. Let that image settle into you as you breathe. A young man in 1965, bending over his calculations, discovering a window into the solar system that had been waiting, unobserved, for 175 years. The planets had been moving toward that alignment since long before he was born. They would have moved through it, and past it whether he noticed or not. But he did notice. And because he noticed, two spacecraft exist that otherwise would not. Voyager 2 launched first. On the 20th of August, 1977, it lifted off from Cape Canaveral on the back of a Titan IA Centaur rocket, rising through the blue Florida sky on a column of fire and noise, and then the noise faded, and the sky darkened around it, and it was free. It was sent along the slower of the two planned trajectories, a longer, more sweeping path that would carry it past all four giant planets. Jupiter first, then Saturn, then Uranus, then Neptune. Each encounter carefully timed, each gravity assist precisely calculated. The engineers called it the Grand Tour trajectory, and it was an act of extraordinary mathematical foresight. Every detail of those four planetary flybys had been worked out years in advance. The angles of approach, the distances, the timing, so that each planet's gravity would catch the spacecraft and redirect it, cleanly and efficiently, toward the next destination. Voyager 2 was not just launched toward Jupiter. It was launched toward a point in space where Jupiter would be by the time it arrived. The same was true of Saturn, and of Uranus, and of Neptune. Each target was a moving point in the future, not a fixed location in the present. The mission required its planners to know, with extraordinary precision, where four distant worlds would be, years from now. There is something almost meditative about that kind of thinking. Not where things are, but where they will be. Trusting the mathematics enough to aim at empty space, knowing that by the time the spacecraft arrives, it will not be empty at all. 16 days later, on the 5th of September, 1977, Voyager 1 followed. It took a different path, faster, more direct, aimed first at Jupiter and then at Saturn's largest moon, Titan, which the scientists considered a priority target because of its thick, mysterious atmosphere. That choice to prioritize Titan had a consequence. The gravity assist from Saturn that Voyager 1 received sent it upward, out of the plane of the solar system, on a trajectory that would carry it above and away from the remaining planets, rather than onward to Uranus and Neptune. Voyager 1 would visit 2 planets instead of 4. But it would visit them sooner, and it would ultimately travel faster, and it is that faster trajectory, that earlier, steeper slingshot, that eventually allowed Voyager 1 to overtake its twin and become the most distant object of human origin in the universe. 2 spacecraft, launched 16 days apart, aimed at different futures, and yet they shared the same origin, the same purpose, the same golden record. In some deep sense, they have always been a pair, 2 voices in the same message, sent in 2 different directions to say the same thing. We were here, we were curious, and we reached as far as we could. As you breathe slowly in the quiet of this moment, think about what it means to plan something at that scale. The engineers and scientists who designed the Voyager trajectories were working with slide rules and early computers, by modern standards, laughably underpowered. They were calculating the positions of planets years and decades into the future, predicting the precise gravitational effects of each flyby, adjusting and refining, and checking their work against the relentless arithmetic of orbital mechanics. They could not afford errors. A spacecraft launched at the wrong angle would miss its gravity assist and drift into the void. Its mission ended before it truly began. Every calculation had to be right. And so they checked and rechecked and ran the numbers again, because the window was narrow and the opportunity was singular, and they understood, in a way that few people ever get to understand anything, that what they were doing would not be possible again in their lifetimes. There is a particular quality to work done under that kind of constraint. It becomes very still, very focused, not frantic, but precise, the way a person becomes very calm when they understand exactly what is at stake and exactly what they need to do. That calmness is what carried Voyager 1 and Voyager 2 off the launch pad and into the dark. Not excitement, not drama, though there was plenty of both, but the deep, settled confidence of people who had done the mathematics and trusted what they found. The planets were ready. The window was open. The spacecraft were built and tested and loaded with their golden records and their cameras and their instruments for measuring magnetic fields and plasma and cosmic rays. The calculations had been made and verified and made again. All that remained was to go, and so they went. Voyager 2 first, climbing through the summer sky on a path that had been imagined for it 12 years before its launch, aimed at a sequence of worlds arranged by the slow clockwork of the solar system into the most favorable configuration, they would form in any living person's lifetime. Voyager 1 16 days later, faster, sharper, climbing toward its own version of the future. Tonight, as your body settles and your breathing finds its own easy rhythm, let yourself rest in the certainty of that. The universe arranged its planets. The mathematics were waiting to be found. A young engineer found them. Decades of work followed. And two small machines rose from the Earth and began a journey that no one then alive would live to see completed. There is something quietly wonderful about that. About beginning something you know you will not finish. About trusting the work and letting it go. The planets that aligned to make Voyager possible are still out there, still turning in their long, slow orbits. By now they have moved on, the alignment long dissolved, the window closed. But the spacecraft that slipped through it are still in motion, still carrying the momentum of those long-ago planetary encounters, still sailing outward through a darkness no instrument from Earth can fully illuminate. They needed only one moment of alignment. One rare, patient, 175-year moment, and they made it count. Let that thought carry you gently now, as sleep draws closer. The universe gives its opportunities quietly and briefly, and to those who are paying attention. Tonight, you don't need to pay attention to anything at all. The window is closed, the spacecraft are away, and somewhere far beyond the reach of any light you will ever see, two small golden messengers are still moving through the dark. Let your eyes grow heavy. Let the stars blur softly at the edges of your mind. The journey continues without you needing to watch. There is a particular kind of wonder that belongs to arrival. Not the planning, not the launching, not the long quiet years of travel in between, but the moment when something that was once only a smudge of light in a telescope lens suddenly resolves into a world. A real world, with weather and color and moons and movement. A place that existed for billions of years before any human eye turned toward it, waiting with absolute patience to be seen clearly for the first time. That is what the Voyager spacecraft gave us. One world at a time. They arrived in one world at a time. The solar system became something more than a collection of points of light. It became a neighborhood strange, vast, wild, and astonishingly beautiful. As you settle deeper into rest, let the story of those arrivals wash over you. There is no need to hold on to every detail. Let the images form and drift, the way scenes form in the early minutes of a dream, vivid and fleeting, real and gone, leaving only a feeling behind. Jupiter was first. By the time Voyager 1 made its closest approach to Jupiter in March of 1979, it had been traveling for 18 months. 18 months of near silence, of instrument checks and trajectory corrections, of patient waiting while the vast distance slowly closed, and then, gradually, the smudge became a disk, and the disk became a world, and the world became the most dramatic thing anyone had ever photographed in space. Jupiter is not subtle. It is the largest planet in the solar system, more than 11 times the diameter of Earth, so massive that all the other planets combined could fit inside it with room to spare. Its surface is not a surface at all, but a churning, banded atmosphere of hydrogen and helium, striped in creams and ochres and deep rusted reds, wrapped in jet streams that move faster than any wind on Earth, and at its southern hemisphere, like an eye that has been open for centuries, the Great Red Spot. Voyager 1 saw it clearly for the first time. Not a smear in a ground-based telescope, but a storm, an actual storm. A swirling anticyclone wider than the entire planet Earth, with winds circling at speeds of hundreds of kilometers per hour. A structure so vast and so old that it had been observed by astronomers since the 1600s and had not stopped spinning in all that time. Let that image float in your mind as you breathe. A storm older than any nation on Earth, older than any living language, churning quietly in the atmosphere of a planet so far from the sun that its light arrives diluted and cold. The Great Red Spot has been there your entire life, your parents' entire lives, and the lives of every person who lived before them for the past 400 years. It was there before the Voyager spacecraft existed, and it is there still, but Jupiter had more to offer than its own dramatic face. As Voyager 1 swept through the Jovian system, its cameras turned to the moons, and what they found there rewrote the textbooks. Io, the innermost of Jupiter's large moons, revealed itself to be the most volcanically active body in the entire solar system. Not gently active violently, spectacularly active. Its surface was covered in sulfur and sulfur dioxide, painted in yellows and oranges and whites, constantly resurfaced by eruptions that hurled material hundreds of kilometers into space. No craters were visible on Io, because the surface was being renewed so rapidly that any crater formed would be buried or melted before it could be recorded. It was a world in constant flux, needed by the gravitational forces of Jupiter, pulling it one way, and the other large moons pulling it another, generating so much internal heat that it leaked continuously from the ground. And then there was Europa, smooth, bright, crisscrossed with long dark lines like cracks in an eggshell. The lines were fractures in an icy crust. Beneath that crust, the scientists suspected, lay a global ocean of liquid water, kept liquid not by proximity to the sun, but by the same tidal flexing that kept Io volcanic. An ocean in the dark, beneath the ice, on a moon orbiting Jupiter. The implications were, and remain, staggering. Voyager 2 arrived at Jupiter 4 months after its twin, in July of 1979, following a slightly different approach path that allowed it to observe regions Voyager 1 had not fully captured. The two spacecraft together built a picture of Jupiter that no single flyby could have provided. A stereo portrait of the most complex system in the solar system beyond the Sun itself. And then Voyager 2 used Jupiter's gravity to begin the next leg of its journey. The great planet reached out with its enormous gravitational field, caught the spacecraft, swung it around, and released it. Faster now, aimed at the golden-ringed world waiting further out in the dark. Saturn. Voyager 1 reached Saturn in November of 1980, and the planet did not disappoint. Saturn is, by many measures, the most visually extraordinary object in the solar system. Its rings, which had been observed from Earth for centuries, ever since Galileo first pointed his telescope at them in 1610 and described them, confused, as ears on either side of the planet, were revealed by Voyager 1 to be structures of breathtaking complexity. From Earth, the rings appear as a few broad bands, separated by visible gaps. Up close, they resolved into thousands of individual ringlets, each one a stream of ice and rock particles, ranging in size from tiny grains to chunks the size of houses, all orbiting Saturn in precise, gravitationally choreographed paths. Some ringlets were braided. Some had sharp edges maintained by the gravitational influence of small shepherd moons. Some regions showed spokes, dark radial structures rotating with the planet's magnetic field in ways that puzzled scientists for years. The rings are extraordinarily thin relative to their width. They span hundreds of thousands of kilometers from inner edge to outer edge, yet in most places they are no more than about 10 to 30 meters thick. If you scaled Saturn's rings to the thickness of a sheet of paper, they would be wider, proportionally, than a large city. Let that image drift through you as your breathing slows. Something impossibly wide and impossibly thin, turning in the cold light of a distant sun, composed of countless billions of individual pieces of ice, each one following its own quiet orbit, together creating something of such beauty that when Galileo first saw it he thought his telescope was broken. Voyager 1's visit to Saturn also included a close approach to Titan, Saturn's largest moon, and the reason Voyager 1's path was designed the way it was. Titan is remarkable. It is the only moon in the solar system with a thick atmosphere denser, in terms of surface pressure, than Earth's. That atmosphere is rich in nitrogen and methane, and it wraps Titan in an orange haze so thick that Voyager 1's cameras could not see through it to the surface below. What lay beneath remained a mystery for decades. But the data gathered about the atmosphere itself was extraordinary complex organic chemistry, a world where methane might cycle through the environment the way water cycles on Earth, raining from clouds onto a surface of ice and hydrocarbon lakes. The decision to target Titan, however, came at a price. The gravity assist Voyager 1 received from Saturn after its Titan encounter bent its path sharply not onward to Uranus and Neptune, but upward, out of the plane of the solar system, away from the remaining planets entirely. Voyager 1's grand tour of the planets was complete. 2 planets visited, 2 transformed from points of light into known worlds. And now its path carried it outward and upward, into the long, unbroken silence beyond. But Voyager 2 was still in the game. When Voyager 2 reached Saturn in August of 1981, it carried with it the accumulated knowledge of everything Voyager 1 had found the year before. Scientists could target their observations more precisely, focus on specific mysteries, choose angles and timings that complemented what had already been learned. Voyager 2 found new details in the ring structure, gathered more data on Saturn's moons, and then crucially threaded a very precise path through the Saturnian system that would set it up for what came next. Its gravity assist from Saturn was aimed not just at a direction, but at a destination. Uranus, a world that, until that moment, had never been visited by anything made by human hands. The wait would be nearly 5 years. On the 24th of January, 1986, Voyager 2 arrived at Uranus. By this point, the spacecraft had been in space for 8.5 years. It had already completed more than any mission planner had originally dared to hope for. But it kept going, and it kept working, and what it found at Uranus was in its quiet way deeply strange. Uranus is tilted. Not just slightly tilted, the way Earth is tilted on its axis, but radically, dramatically tilted. Its axis is inclined at 98 degrees, meaning that it essentially rolls around the Sun on its side. No one is entirely certain why. The most widely accepted explanation is that something very large, perhaps a protoplanet, struck Uranus early in the solar system's history and knocked it onto its side, where it has remained ever since. The result is a planet of extremes. Its poles experience seasons of continuous daylight or continuous darkness lasting decades at a time. Its magnetic field is not aligned with its rotation axis, creating an asymmetric, chaotic magnetic environment unlike anything elsewhere in the solar system. Its moons, too, were strange, their surfaces showing a mixture of ancient cratered terrain and younger, disrupted regions suggesting violent geological histories. One moon, Miranda, appeared to have been shattered and reassembled, its surface a patchwork of wildly different terrains jumbled together as though by some catastrophic ancient impact. Uranus had been a featureless blue-green disk in the best Earth-based telescopes. Voyager 2 turned it into a world. And still it kept going. On the 25th of August, 1989, 12 years after leaving Earth, Voyager 2 reached Neptune. Neptune had been known to exist since 1846, discovered mathematically before it was ever directly observed, predicted by the slight wobble it caused in the orbit of Uranus. For over a century, it had been nothing more than a blue disk in the telescope, its details hidden by distance and the blurring effects of Earth's atmosphere. Voyager 2 changed all of that in a few short hours of closest approach. Neptune revealed itself to be an unexpectedly dynamic world. A deep, vivid blue, the result of methane in its atmosphere absorbing red light, with wind speeds that dwarfed everything measured elsewhere in the solar system. Winds of more than 2,000 kilometers per hour, moving in the opposite direction to the planet's rotation. A massive dark storm system, reminiscent of Jupiter's Great Red Spot, that the mission team named the Great Dark Spot. And above Neptune's south pole, a moon called Triton, orbiting backwards, moving in the opposite direction to the planet's rotation. A strong sign that it did not form alongside Neptune, but was captured from elsewhere, perhaps from the distant belt of icy bodies beyond. On Triton's surface, geysers of nitrogen erupted from beneath the ice, shooting dark material kilometers into the thin atmosphere. Geysers. On a moon at the edge of the solar system, with a surface temperature of minus 235 degrees Celsius. The solar system, it turned out, was stranger and more alive than anyone had imagined. With its Neptune encounter complete, Voyager 2 joined its twin on an outward trajectory that would carry it beyond the planets forever. It had done something no spacecraft had done before, visited all 4 giant planets in a single mission, and would never be repeated in the same way, because the alignment that made it possible had already closed. One spacecraft for worlds 12 years. The only grand tour in human history. As your breathing slows now, and the images from this long journey begin to soften and blur at the edges, let yourself hold the quiet enormity of what these two machines accomplished. They arrived at worlds that had existed for billions of years in darkness and silence, worlds that had never been anything more than lights in the sky, and they brought them close enough to see. Jupiter and its volcanic moons, Saturn and its impossible rings, Uranus tilted on its side, Neptune roaring with the fastest winds in the solar system. All of it seen, all of it known, all of it transformed by two small spacecraft and the rare patience of a planetary alignment, from mystery into memory. And now both probes sail beyond all of it, past the last planet, past the last moon, into the long, dark, featureless quiet of interstellar space. The adventure is not over. It has simply changed shape. Let your eyes grow heavy now. Let the planets drift past in the soft space behind your eyes, vast, colored, turning slowly in the dark. You have traveled far tonight already. Rest here for a while. There is still so much further to go. There is a particular feeling that comes at the end of a long journey outward. Not the excitement of departure, which belongs to the beginning. Not the wonder of arrival, which belongs to the middle. But something quieter than both of those, a feeling that arrives gradually, almost without announcement, as the familiar things grow smaller behind you and the unfamiliar things ahead have not yet taken shape. It is the feeling of the threshold, the in-between, the place where one world ends and another has not yet begun. That is where we are now in this story. The planets are behind the Voyager spacecraft. Jupiter, Saturn, Uranus, Neptune all visited, all transformed from mysteries into memories, all now receding slowly in the distance. The grand tour is complete. The cameras that photograph those worlds have been powered down to conserve energy. The instruments that will matter now are different ones, quieter instruments, designed not to photograph the dramatic, but to measure the subtle. Magnetic fields, charged particles, the behavior of the solar wind at the very limits of its reach. And the reach of the sun, it turns out, is extraordinary. As you breathe here in the quiet, let your mind drift outward past Neptune, past the last of the planets, past the cold, dark region of space, where the Kuiper belt spreads its population of icy bodies in slowly orbiting clouds. Let the sun shrink behind you, slowly, until it is no longer a disk, but a point, still the brightest point in the sky, still unmistakably the center of everything, but diminished now, reduced by distance to something closer to a very bright star than to the overwhelming presence it is from Earth. Even here, at this enormous distance, you have not yet left the sun's domain. Because the sun does not end where its light fades. The sun is not a quiet object. It is continuously, ceaselessly active, not just burning, but exhaling. From its surface, the sun releases a constant stream of charged particles, protons, electrons, helium nuclei, all flowing outward at hundreds of kilometers per second in every direction. This stream is called the solar wind, and it is not a metaphor. It is a real, physical flow of matter, continuously pouring outward from the sun into the surrounding space, filling the volume around our star the way breath fills a balloon. And like breath in a balloon, it pushes outward until something pushes back. In the space between the stars, there is material, thin, diffuse, cold but present. The interstellar medium, as astronomers call it, is not empty. It is threaded with gas and dust and magnetic fields, the accumulated exhaled matter of long-dead stars, and the primordial material left over from the earliest ages of the galaxy. It exists at its own pressure, its own density, flowing in its own slow currents through the vast spaces between stellar systems. The solar wind flows outward. The interstellar medium pushes inward. And somewhere, at some distance from the sun that depends on the balance of pressures between the two, they meet. The region carved out by the solar wind, the vast bubble of space within which the sun's influence dominates, is called the heliosphere. And it is far, far larger than most people imagine. Picture the solar system as you know it. The sun at the center. The 8 planets arranged in their orbits, the outermost of them, Neptune, at a distance of about 30 astronomical units. That whole familiar structure, everything we think of when we think of the solar system, fits comfortably within the inner heliosphere. But the heliosphere itself extends to roughly 100 astronomical units from the Sun, more than 3 times the distance to Neptune. In some directions, where the solar wind is stronger or the interstellar medium thinner, it may extend even further. The heliosphere is not a perfect sphere. It is more like a bubble being pushed through water, elongated in the direction of the Sun's motion through the galaxy, compressed on the leading edge where it meets the oncoming interstellar medium. For years and decades after leaving Neptune behind, both Voyager spacecraft were still inside this bubble. Still inside the Sun's extended atmosphere, in a sense. Still within the domain of our star's influence, carried along by the solar wind even as they moved at extraordinary speed away from the Sun itself. The heliosphere was their ocean, and they were crossing it, slowly, steadily, toward the far shore. Let that image rest in you for a moment. An ocean of solar wind, vast beyond easy comprehension, surrounding the Sun and everything that orbits it in an enormous protective bubble. Because that is, in a meaningful sense, what it is, protective. The heliosphere shields the inner solar system from a significant portion of the cosmic radiation that fills interstellar space. Outside the heliosphere, the galaxy is threaded with high-energy cosmic rays, particles accelerated to enormous speeds by distant supernovae and other violent events, that travel freely through interstellar space. Inside the heliosphere, the solar wind and the magnetic field it carries deflect a substantial fraction of these rays, reducing the radiation environment within the bubble compared to the space outside it. The Earth exists inside this shield. Every living thing on this planet has evolved within the protection of the heliosphere, and most of us have never thought about it for a single moment of our lives. It is invisible, intangible, extending far beyond anything we will ever visit. And yet it is, in a quiet way, one of the things that makes life here possible. The Voyager spacecraft were heading toward its edge, heading toward the place where that protection ends, and the raw interstellar environment begins. The boundary itself is not a sharp line. It does not end the way a wall ends. It tapers and transitions, a gradual thickening of the interstellar medium, a gradual weakening of the solar wind, a series of boundaries and transition zones, rather than a single clean edge. The first of these boundaries is called the termination shock. At the termination shock, the solar wind, which has been flowing outward at several hundred kilometers per second, abruptly slows. It slows because it is running into the resistance of the interstellar medium, piling up the way a river current piles up when it meets a lake. The particles in the solar wind don't stop, but they slow dramatically, and they become more compressed and turbulent. The smooth, fast-flowing solar wind becomes something messier and more chaotic. Beyond the termination shock lies a region called the heliosheath, the outer layer of the heliosphere, where the slowed and compressed solar wind fills the space between the termination shock and the final boundary of the Sun's domain. The heliosheath is vast, tens of astronomical units thick in some directions, a turbulent, magnetically complex region that the Voyager spacecraft would spend years crossing. And beyond the heliosheath, the final boundary, the heliopause. The heliopause is where the solar wind stops entirely, where the pressure of the interstellar medium and the pressure of the solar wind reach equilibrium, where, for the first time, the material around a spacecraft is no longer material that came from the Sun. That is the true edge of the solar system, in the most meaningful physical sense. Not the orbit of Neptune, not the outer reaches of the Kuiper belt, not even the distant shell of cometary material that astronomers call the Oort cloud, but the heliopause, the place where the Sun's breath ends and the breath of the galaxy begins. The Voyager spacecraft did not know they were approaching this boundary. They carry no consciousness, no anticipation. But the scientists tracking them from Earth were watching the data carefully, watching the instruments that measured the speed and density of the solar wind, the strength and direction of the magnetic field, the count of energetic particles arriving from outside the heliosphere. The numbers were changing. Slowly, year by year, the signatures in the data were shifting. The solar wind was slowing. The particle counts from outside were rising. The magnetic environment was growing more complex. The threshold was ahead. Both spacecraft were still years away from crossing it. Voyager 1 ahead, always ahead, pushing further and faster into the dark. Voyager 2 following on its own path, its own instruments gathering its own complementary record of the same vast transition zone. But the approach had begun. There is something about the idea of a threshold that speaks to the part of us that understands sleep. Because sleep too is a threshold, a boundary between one kind of existence and another. On one side, the world of wakefulness, the thoughts and sensations and memories and plans, the noise and light and movement of conscious life. On the other side, something quieter and stranger and harder to describe. A place where the rules are different, where time moves differently, where the self becomes less defined, where the ordinary limits of experience dissolve. And the crossing is never a single moment. It is a gradual transition, a dimming, a softening, a letting go. The thoughts grow less coherent. The body grows heavier. The sounds of the room become distant, and then more distant still, until they are only a faint background texture. And then they are gone. That is what the Voyager spacecraft were approaching. Their own threshold. Their own gradual transition from one kind of space to another. Inside the heliosphere, the familiar. The solar wind, the sun's magnetic field, the environment shaped by our star. The territory that the sun has claimed, in a sense, by filling it with its own material. Outside, something else entirely. Not frightening. Not hostile, in any dramatic sense. Just different. Older. Quieter. The space between the stars, which has existed largely unchanged since long before the sun was born, filled with the ancient exhaled matter of stars that lived and died before our solar system existed. As you lie here in the quiet, and the sounds of the world beyond this room grow softer and less distinct, and your body settles deeper into the comfortable weight of rest, let the Voyager spacecraft sail on ahead of you into that transition. They have been in space for years now in this part of the story. A decade. More than a decade. Moving at speeds that would cross a continent in minutes, and yet making only the slowest progress against the vast indifference of cosmic distance. Patient, steady, unrelenting. The heliosphere stretches around them like an ocean they cannot see, defined not by any visible boundary, but by the behavior of particles too small for any human eye to detect. The instruments are registering everything. Every fluctuation in the solar wind. Every cosmic ray arriving from outside. Every shift in the magnetic field. The data flows back to Earth at the speed of light. And even at the speed of light, it takes hours to arrive. Hours of travel, across the expanding distance, from a spacecraft that is itself moving, to a planet that is also moving, around a star that is also moving through the galaxy. The mathematics of tracking the Voyager spacecraft across those distances, maintaining contact, knowing where they are and how to aim an antenna at them. This is itself a kind of extraordinary human achievement, quiet and technical and profound. But tonight, there is no need to hold all of that complexity. Let it soften. Let the solar wind carry you. Let the boundary draw nearer, slowly, as it drew nearer for the Voyager spacecraft across years of patient travel. Not rushing, not forcing, just moving steadily toward the place where one thing ends and another begins. The threshold is ahead, and the crossing, when it comes, will be unlike anything that has come before. Some moments in history are loud. They announce themselves with fire and noise, and the held breath of crowds. They are witnessed in real time, broadcast and celebrated, marked immediately as the things they are. The launch of a rocket, the first step onto the moon, the roar of engines, and the crackle of a radio transmission crossing 250,000 miles of space. But some of the most profound moments in human history are quiet. They are discovered in data, in numbers on a screen, in the careful, patient reading of instruments by scientists who have been waiting, not for hours, not for days, but for decades, for a particular set of measurements to shift in a particular way. And when the shift finally comes, it comes not with a sound, but with a stillness, a recognition, a moment of looking at the numbers and understanding, with complete certainty, that something has just changed forever, The moment Voyager 1 crossed into interstellar space was one of those quiet moments. And it was, in its quietness, one of the most extraordinary things that has ever happened. Let your body grow heavier as you breathe. Let the weight of the blanket, the softness of the surface beneath you, the warmth of the air around you, let all of it press gently downward, anchoring you here while your mind drifts outward to follow the story. We left the Voyager spacecraft approaching the edge of the heliosphere, that vast bubble of solar wind that surrounds our star and everything that orbits it. We talked about the termination shock, where the solar wind slows, about the heliosheath, the turbulent outer layer of the bubble, about the heliopause, the final boundary, where the sun's breath ends entirely. Now we arrive at the crossings themselves. Voyager 1 reached the termination shock in December of 2004, 27 years after launch. More than a quarter of a century of travel, at speeds that would seem impossibly fast by any human standard. And yet the solar system had been so vast that it had taken all of that time just to reach the first boundary zone of the heliosphere. The termination shock, as the name suggests, is where the solar wind meets its first major obstacle, the pressure of the interstellar medium pushing back. The solar wind, which has been streaming outward from the sun at between 400 and 800 kilometers per second, abruptly slows to roughly a quarter of that speed. It doesn't stop, but it transitions from a smooth, fast supersonic flow to something slower, denser, hotter, and more turbulent. The instruments on Voyager 1 measured this transition. The scientists at the Jet Propulsion Laboratory, watching the data arrive with its hours-long delay, saw the signature clearly. The particle counts changed. The magnetic field shifted. The numbers told a story, and the story was, we are crossing a threshold. Voyager 1 crossed the termination shock at a distance of roughly 94 astronomical units, from the Sun 94 times the distance from the Earth to the Sun. A number so large it resists easy imagination, yet still, inside the heliosphere. Still inside the Sun's extended domain. The spacecraft entered the heliosheath, that outer turbulent layer, and continued outward. Nearly 3 years later, in August of 2007, Voyager 2 crossed the termination shock as well. Because Voyager 2 was traveling on a different trajectory than its twin, crossing the termination shock at a different angle, a different region of the heliosphere's asymmetric boundary. Its crossing happened at a slightly different distance, around 84 astronomical units. The heliosphere, it turned out, was not uniform. The boundary was closer in some directions than others, shaped by the pressure of the interstellar medium and the varying output of the solar wind over time. This difference was not a disappointment, it was a gift. Having 2 spacecraft cross the termination shock at different locations and different times meant that scientists could begin to map the shape of the boundary, to understand its variability, to compare the conditions measured by one probe against those measured by the other. 2 data points instead of 1. 2 windows onto the same enormous phenomenon. Both spacecraft were now in the heliosheath, pushing through that thick outer layer of compressed, turbulent solar wind, their instruments measuring the changing environment around them. The heliopause lay ahead, still years away, still uncertain in its exact location, its precise nature still a matter of scientific debate. The long approach continued. For Voyager 1, the years in the heliosheath were full of surprises. The environment there was stranger and more complex than many models had predicted. The magnetic field was turbulent and variable. The charged particle environment fluctuated in unexpected ways. And in the months leading up to the final crossing, the instruments began registering dramatic changes that told the scientists something momentous was close. The low-energy particles from the solar wind began to drop away. Not gradually, sharply, as though a door was closing behind the spacecraft, cutting off the flow of solar material. Simultaneously, the count of high-energy cosmic rays from outside the heliosphere spiked upward. Particles that had been largely excluded by the heliosphere's protective bubble were now arriving freely, from all directions, at levels the instruments had not previously recorded. The magnetic field shifted in direction. And then, in the summer of 2012, The measurements crossed a threshold that the scientists had been watching for across decades of patient observation. The solar wind particles essentially disappeared. The cosmic rays stabilized at their new, higher level. The magnetic field settled into a new orientation, aligned not with the sun's influence, but with the galactic magnetic field beyond. Voyager 1 had crossed the heliopause. The announcement, when it came, was careful and measured, as scientific announcements tend to be. There was debate about exactly when the crossing had occurred, about how to interpret specific features of the data, about what precisely the instruments were telling them. Science moves carefully, checking and rechecking, resisting the temptation to claim more than the evidence supports. But the evidence, when all of it was assembled and reviewed, was clear. In August of 2012, Voyager 1 crossed the heliopause. It moved from the outer layer of the heliosphere into the interstellar medium, the space between the stars. It became, at that moment, the first object of human origin to leave the Sun's kingdom and enter the galaxy beyond. 35 years after launch. 35 years of travel, of patient instrument readings, of antenna dishes on Earth tracking a signal growing fainter with every passing year. 35 years from a Florida launch pad to the boundary of interstellar space. Let that number settle over you like something warm and heavy. 35 years. Children born the year Voyager 1 launched were middle-aged when it crossed the heliopause. The engineers who built it had retired. Carl Sagan, who had championed the mission and overseen the creation of the Golden Record, had been dead for 16 years. The world had changed almost beyond recognition in the time between launch and crossing. And throughout all of it, through the Cold War and its end, through the rise of the Internet, through decades of human joy and suffering and transformation, Voyager 1 had simply kept moving. Steadily, silently, outward. There is something almost impossible to hold in the mind about that crossing. Not the technical details, those are remarkable enough, but the meaning of it. The heliopause is not just an interesting measurement. It is the edge of our star's direct influence on the universe. It is the boundary beyond which the sun no longer shapes the immediate environment. Beyond the heliopause, the material around Voyager 1 was no longer solar material. It was interstellar material, ancient, cold, filling the void between stellar systems, unchanged in its fundamental nature since long before the Earth existed. On one side of that boundary, the sun's kingdom, a bubble of space that our star has carved out of the galaxy by the force of its own continuous exhalation, maintained for as long as the sun has burned, destined to persist for as long as it continues to burn. On the other side, the galaxy itself. Voyager 1 crossed from one into the other. A human-made machine, carrying a golden record of music and voices and whale song and the sound of rain, sailing into interstellar space. Voyager 2 followed. On the 5th of November, 2018, more than 6 years after its twin, Voyager 2 crossed the heliopause and entered interstellar space. It became the second human-made object to achieve this, and the data it provided was, if anything, even more scientifically valuable than Voyager 1's crossing had been. Because Voyager 2 still had a functioning plasma science instrument that Voyager 1's had long since stopped working. This meant that when Voyager 2 crossed the heliopause, scientists received direct measurements of the plasma, the ionized gas, on both sides of the boundary. They could measure the temperature, density, and composition of the solar wind on the inside and compare it to the properties of the interstellar plasma on the outside. What they found was a boundary sharper than expected. The heliopause was not a broad, gradual transition, but something more like a wall, a relatively thin region where the solar wind plasma ended and the interstellar plasma began, the two environments largely separated rather than extensively mixed. Cold outside, much hotter plasma on the inside, in the heliosheath. A magnetic field that changed direction at the boundary. 2 spacecraft, 2 crossings, 6 years and billions of kilometers apart. And together, they had given humanity its first direct measurements of the environment on both sides of the edge of the solar system. As you breathe here in the quiet, let the magnitude of that drift through you without needing to hold it tightly. Two machines, built in California in the early 1970s, designed to last perhaps 5 years and visit 2 or 4 planets, had instead kept working for decades, crossed the entire span of the planetary solar system, traversed the vast outer heliosphere, and sailed through the heliopause into interstellar space. They are there now, both of them, in interstellar space, in the space between the stars, in the ancient dark that exists beyond the sun's reach. Their instruments are still working, still sending data, still measuring the environment of a region that no probe has ever measured before. The golden records they carry, those 12-inch discs of gold-plated copper, engraved with the sounds and images of a world 4 decades and more than 20 billion kilometers behind them, are now in interstellar space. The music of Bach and Beethoven and Chuck Berry, the sound of a mother's first words to her child, the call of the humpback whale. All of it is in the space between the stars, moving outward, moving quietly, as the universe watches in its vast and unhurried way. The night is deep now, and your breathing is slower, and the thoughts that were sharp and demanding earlier in the evening have softened into something easier to carry. The crossings are complete. The boundary has been passed. Both Voyager spacecraft are in interstellar space tonight. Right now, as you lie here, they are out there, beyond the heliopause, beyond the sun's kingdom, in the oldest and quietest space there is. There is no wind where they travel. No solar wind, no planetary weather, no aurora or storm or season. Just the slow, cold, ancient drift of interstellar material, and the 2 small machines moving through it, measuring, transmitting, enduring. They crossed the threshold, and on the other side, they found exactly what they had always been heading toward. The galaxy. Let your eyes grow heavy now. Let the boundary dissolve behind you the way all boundaries dissolve in sleep. Quietly, gradually, without announcement. One moment you are on one side. Then, without quite knowing when it happened, you are on the other. That is the crossing. That is always the crossing. Right now, as you lie here in the dark, something is happening. Not somewhere dramatic. Not in a laboratory, or a control room, or a launch facility, lit up with the noise and spectacle of a rocket leaving the ground. Something is happening in a place so remote and so silent that the word quiet does not begin to describe it. In a region of space where no human being has ever been, and no human being is likely to go within any time frame we can meaningfully imagine. Right now, 2 spacecraft are moving through interstellar space. Not heading toward it. Not approaching it. In it. Immersed in the ancient, cold, thinly threaded medium that fills the vast distances between the stars. Their instruments are active. Their antennas are pointed, with extraordinary precision, toward a small blue planet billions of kilometers behind them. Their signals are traveling toward us at the speed of light, taking more than 20 hours to complete the journey. And when those signals arrive, when the enormous dish antennas of NASA's Deep Space Network catch the faint whisper of data crossing that impossible distance, they carry information that no instrument in human history has ever gathered before. The Voyager spacecraft are not museum pieces. They are not relics. They are active explorers, working right now, in a place no probe has ever been, sending home a continuous record of what it is like to exist beyond the edge of the sun's kingdom. Let that thought settle into you as your breathing deepens. They are out there tonight, moving, measuring, transmitting. Right now, Voyager 1 has been sampling the local interstellar medium since it crossed the heliopause in 2012. That is more than a decade of continuous measurement, more than 10 years of data gathered from a region of space that, before August of 2012, was entirely unknown to direct observation. What it has found is a place of extraordinary subtlety. The interstellar medium is not empty. It never was. Astronomers had known for a long time that the space between stars is threaded with gas and dust and magnetic fields, the dispersed remnant material of ancient stellar processes. But knowing something from theory and measuring it directly are very different things. Voyager 1's instruments have been providing the first ground truth measurements of the local interstellar environment. The actual particle counts, the actual magnetic field strengths and directions, the actual plasma density of the space that surrounds our solar system. And one of the things those measurements have revealed is that the heliosphere leaves a mark. Our Sun, in carving out its bubble of solar wind, does not simply displace the interstellar medium. It distorts it. The magnetic field lines that thread through the interstellar medium ancient, galaxy-spanning structures, shaped by the accumulated effects of countless stars and supernova explosions, and the slow rotation of the Milky Way itself, are bent and compressed where they meet the heliosphere. The bubble of the Sun's influence pushes against the interstellar magnetic field and drapes it, deflecting it from its natural direction, piling it up at the boundary the way water piles up around a stone in a stream. Voyager 1's measurements have helped reveal the scale and character of this distortion. The magnetic field in the local interstellar medium, near the heliopause, is not pointing in the direction the galactic field would suggest it should. It has been pulled and shaped by the presence of the heliosphere, by the Sun's continuous outward push, into a configuration that reflects the geometry of the boundary it has encountered. This matters more than it might first seem. It means that the heliosphere is not merely a passive bubble sitting in the interstellar medium, but an active participant in shaping its local environment. Our Sun reaches out beyond its own boundary and rearranges the space around it. The solar system has a presence in the galaxy that extends even beyond the heliopause. As NASA scientists look at the data and continue to build their models, they expect that Voyager 1 will eventually travel far enough from the heliosphere that it moves beyond this distorted region into a part of the interstellar medium that is genuinely pristine, genuinely undisturbed by the Sun's influence. A region where the magnetic field runs in its true galactic direction, where the plasma has not been compressed or redirected by anything our star has done. Voyager 1 has not reached that region yet, but it is heading there. And when it does, the measurements will change again, another threshold, another transition, another window opening onto a deeper understanding of the space between the stars. Meanwhile, in a different part of the sky, Voyager 2 is gathering its own record. This is one of the quiet miracles of the Voyager program, the fact that the two spacecraft are not traveling in the same direction. They diverged long ago, their different planetary trajectories sending them on paths that now carry them to entirely different regions of the interstellar medium. They are exploring not a single point, but two widely separated locations, giving scientists a comparative view that no single spacecraft could ever provide. Voyager 1 crossed the heliopause, heading generally upward out of the plane of the solar system, the broad, flat disk in which the planets orbit, moving toward the part of the sky occupied by the constellation Ophiuchus, the Serpent-Bearer, a large constellation that straddles the celestial equator. From our perspective on Earth, Ophiuchus is a summer constellation, sitting in the direction of the galactic center. That is broadly where Voyager 1 is headed, not toward any specific star, but into that vast region of the sky. Voyager 2 is heading in the opposite direction downward, below the plane of the solar system, toward the southern sky and the faint constellation of Telescopium. A small, unremarkable constellation to human eyes, offering no bright stars to anchor a story, but now forever associated with the direction from which one of humanity's greatest journeys is departing. Above the plane and below it, two different samples of the interstellar medium, gathered simultaneously on opposite sides of the solar system's disk. Two voices in the same conversation, speaking from different rooms, allowing scientists to understand something about the shape and variation of the environment that neither voice alone could reveal. The numbers that describe their movement are, in their quiet way, staggering. Voyager 1 is currently traveling at roughly 17 kilometers per second relative to the Sun's 17 kilometers every second. In the time it takes you to draw a single slow, easy breath, the kind of breath you are drawing right now, unhurried, the breath of a body settling into rest, Voyager 1 has moved more than 100 kilometers further from the Sun. In an hour, it covers more than 60,000 kilometers. In a day, more than 1.4 million. In a year, more than 500 million kilometers. And yet, measured against the distances of interstellar space, this is a crawl. The nearest star system to our own, the Alpha Centauri system, home to 3 stars bound together by gravity, is approximately 4.2 light-years away. A light-year is the distance light travels in a year, moving at 300,000 kilometers per second. At Voyager 1's current speed of 17 kilometers per second, it would take the spacecraft approximately 73,000 years to cover that distance if it were headed that way, which it is not. Voyager 2 moves slightly slower, roughly 15.5 kilometers per second relative to the Sun. The difference in speed is a legacy of their different trajectories, their different planetary encounters, the different amounts of gravitational energy they borrowed from the giant planets during the Grand Tour. Voyager 1 got a more powerful boost. It has been faster ever since. Both are moving. Both are moving right now. And the distances separating them from the Sun increase with every passing second, every passing minute, every hour of this quiet night. There is something grounding about the specificity of those directions. Ophiuchus, telescopium. We look up at the night sky, and we see constellations, patterns that ancient cultures named and mapped and told stories about, arrangements of light that are, in truth, entirely accidental, stars at vastly different distances from Earth that happen to appear near one another from our particular vantage point. The stars of Ophiuchus are not close to one another in space. They are scattered across hundreds of light-years of depth, appearing as a coherent pattern only from the specific location of our small planet. And yet, those are the directions. Those are the patches of sky that, if you were to step outside tonight and look up, you could point toward and say, that is where Voyager 1 is going. Not to any star within those constellations. The stars are too far, the journey too long, the universe too vast for anything to be said about arrival. But the direction is real, and the motion is real, and the spacecraft is real, and it is moving. Right now it is moving. Toward Ophiuchus, above the plane of the planets, through the ancient and undisturbed dark of interstellar space. The data that both spacecraft send back is, by any modern standard, achingly slow. Their transmitters, still running on the original power systems, now significantly reduced after decades of radioactive decay, broadcast at about 160 bits per second at the distances now involved. To put that in perspective, a modern internet connection can transfer millions of bits per second. Voyager's signal, spread across billions of kilometers of space and arriving at Earth already weakened to nearly nothing, carries its information at a rate that would have seemed primitive even to the earliest home computer users of the 1980s. And yet it is enough, because what the spacecraft are measuring changes slowly. The interstellar medium does not rush. Its fluctuations are gentle, gradual, occurring over timescales of days and weeks rather than milliseconds. The data rate that was carefully designed into the spacecraft, optimized for the instruments they carry and the environment they were designed to measure, is still, astonishingly, adequate to the task. The Deep Space Network, the global system of enormous dish antennas that tracks the Voyager spacecraft and receives their signals, is one of the unsung marvels of human engineering. Antennas up to 70 meters in diameter, positioned at sites in California, Spain, and Australia to ensure continuous coverage as the Earth rotates, aimed with extraordinary precision at targets whose exact positions require constant recalculation as both the spacecraft and the Earth move through space. To aim a 70-meter dish at a spacecraft 20 billion kilometers away, moving at 17 kilometers per second, while the Earth rotates beneath the antenna, this is routine, now. It has been routine for decades, but it should not be taken for granted. It is a feat of continuous, daily precision that allows human beings to maintain a conversation with machines at the edge of interstellar space. Step outside tonight, if you can hold the image in your mind without fully waking or simply let it form behind closed eyes. Step outside and look up. Find the soft darkness between the stars. Let your eyes unfocus until the sky becomes a single field of depth rather than a collection of points. Somewhere up there above the plane, heading toward Ophiuchus Voyager, one is moving through a darkness more complete than anything on Earth. The sun behind it is a bright star, still the brightest in its sky, but no longer a sun in any felt sense. The interstellar medium around it is cold and thin, far thinner than the best vacuum achievable in any laboratory on Earth, and yet not nothing. Particle by particle, magnetic field line by magnetic field line, Voyager 1's instruments are reading it, recording it, sending it home. And somewhere in the southern sky below the plane, heading toward telescopium Voyager 2, is doing the same thing. A different direction. A different slice of the interstellar medium. The same patient, continuous, extraordinary work. Together, they are drawing the first map of the space beyond the sun. Not a visual map, their cameras are long since switched off, but a physical map. A map of particles and fields and pressures and temperatures, built data point by data point across years of slow travel through a region of the universe that has never before been directly explored. They're doing it right now. And tonight, as you let your awareness soften and the day releases its hold on you, the work continues. The signals travel. The antennas listen. The scientists read the numbers and understand a little more about the space between the stars than they did yesterday. There is something deeply restful about that. About knowing that the work is being done, quietly and continuously, without drama or announcement. About knowing that out there in the dark, two small machines are still going, still measuring, still sending. You don't need to do anything. Just breathe. Just rest. The Voyagers are watching the universe for all of us tonight. There is a particular kind of beauty that belongs only to things that are ending. Not the beauty of destruction, nothing here is being destroyed. And not the beauty of loss, exactly, though there is something of loss in it. It is quieter than either of those. It is the beauty of a candle that has been burning for a very long time, whose flame is still steady and true, but whose wax is nearly gone. You look at it and you feel two things simultaneously: gratitude that it has burned this long, and the soft, inevitable awareness that it will not burn forever. That is where the Voyager spacecraft are now. Still moving. Still transmitting. Still doing science at the edge of interstellar space, in a region of the universe no instrument has ever measured before. But the power that keeps them alive, that runs their instruments and heats their electronics, and drives the transmitters that send their signals across 20 billion kilometers of dark, is fading. Slowly, steadily, year by year, degree by degree. The candles are still burning, but the wax is nearly gone. To understand what is happening, it helps to understand what has been keeping the Voyager spacecraft alive for nearly 50 years. They do not carry solar panels. At the distances they travel, sunlight is far too faint to be a useful energy source. By the time you reach Jupiter, the sun's light has already dropped to about 4% of its intensity at Earth. By Saturn, it is barely 1%. At the distances Voyager now travels, more than 160 astronomical units from the Sun, the light is so diluted as to be essentially useless for power generation. Instead, both spacecraft carry radioisotope thermoelectric generators, 3 of them each. These devices, compact, robust, requiring no moving parts, no fuel combustion, no external energy source, generate electricity from the heat produced by the natural radioactive decay of plutonium-238. As the plutonium decays, it releases heat. That heat is converted, through a process called the Seebeck effect, into electrical current. Simple, reliable, and extraordinarily long-lived. When the Voyager spacecraft launched in 1977, their radioisotope generators were producing roughly 470 watts of electrical power each. Enough to run a modest collection of household appliances. Enough, crucially, to power all of the spacecraft's scientific instruments, heating systems, computers, and transmitters simultaneously. But plutonium-238 decays continuously. Its half-life is approximately 87.7 years, meaning that every 87.7 years, half of the remaining plutonium transforms into other elements, releasing heat in the process, but becoming something other than a power source. The generators do not fail suddenly. They wind down, gradually, losing roughly 4 watts of electrical output every year. 4 watts per year does not sound like much, but across 5 decades, it accumulates. The Voyager spacecraft are now generating only around 40% of the power they had at launch. And that number continues to fall. Let your breathing slow as you hold that image. The slow, patient, inevitable winding down. Not a failure. Not a malfunction. Simply the nature of radioactive decay. One of the most fundamental processes in the universe, proceeding at its own pace regardless of what anyone wishes or plans or hopes. The engineers at NASA have been managing this gradual power loss with extraordinary care and ingenuity. As the available power has decreased, they have made difficult decisions about which systems to keep running and which to turn off. Heaters that once kept electronic components warm in the cold of deep space have been switched off, one by one, accepting the risk of damage to components that were never designed to operate at such low temperatures. Some have survived. Some have not. Scientific instruments have been powered down as well. The Voyager spacecraft launched with a suite of instruments designed for planetary exploration: cameras, infrared radiometers, ultraviolet spectrometers, instruments optimized for the kinds of measurements you need when flying past Jupiter or Saturn. Most of these have long since been switched off. The cameras were turned off in 1990, after Voyager 1 took its final family portrait of the solar system. The famous image in which Earth appeared as a pale blue dot, a mote of dust suspended in a sunbeam, almost invisible against the vastness around it. What remains now is a reduced, but still scientifically vital set of instruments, the ones best suited to measuring the interstellar environment: the plasma wave subsystem, the magnetometer, the cosmic ray subsystem, the low-energy charged particle instrument. These are the instruments still gathering data, still sending it home, still telling the story of the space between the stars. But even these will eventually have to go. NASA's engineers project that the Voyager spacecraft will be able to continue operating scientific instruments, at least some of them, until sometime in the 2030s. The exact date is uncertain. It depends on how the power continues to decline, on which instruments prove most resilient to the cold and the years, on the difficult judgments that will continue to be made about how to allocate the dwindling supply of what's between heating and science and communication. But the trajectory is clear. Sometime in this decade, perhaps sooner than we expect, perhaps a few years later, the last scientific instrument aboard Voyager 1 will be switched off for the final time. And then, not long after, the transmitter itself will fall silent. The signal that has been crossing the solar system and beyond for nearly 60 years, growing fainter and fainter until the noise of space swallows it entirely. And after that, silence. Not the silence of destruction. The spacecraft will still be there. Still intact, in all likelihood, drifting through the interstellar medium on trajectories that will carry them through the galaxy for millions of years. The golden records will still be attached to their sides, still carrying their cargo of music and voices, and the sounds of a living world. The plutonium in the generators will still be decaying, producing heat that is now too little to power anything, but will persist for centuries more. But the voice will be gone. The conversation between humanity and its two farthest ambassadors, a conversation that has lasted continuously since 1977, will come to an end. There is a particular poignancy to the fact that this conversation has lasted as long as it has. Think about what 1977 means. The world that launched Voyager 1 and Voyager 2 was, in almost every material sense, unrecognizable from the world of today. There was no internet. There were no mobile phones. The computers used to track the spacecraft and process their data filled entire rooms and performed calculations that a modern wristwatch could do in a fraction of a second. The Cold War was at its height. The world's population was roughly 4 billion, about half of what it is now. And in that world, 2 spacecraft were launched. And they have been in continuous contact with Earth ever since. Through everything. Through the fall of the Berlin Wall and the collapse of the Soviet Union. Through the birth of the Internet and the transformation of human communication. Through wars and disasters and the slow, imperfect, ongoing work of human civilization. Through the careers and retirements and deaths of the engineers who built the spacecraft. Through the childhoods adulthoods, and old ages of the scientists who have spent their careers tracking them. The signal from Voyager 1 has been arriving, without interruption, for nearly 50 years. A whisper from interstellar space, crossing 20 billion kilometers at the speed of light, arriving at the dish antennas of the deep space network and being translated into data and understood. That whisper is still arriving tonight. But let us sit with the ending that is coming, because it deserves to be sat with. There is a team of people at NASA's Jet Propulsion Laboratory whose work is intimately tied to the Voyager spacecraft. Scientists who have dedicated years or decades of their professional lives to these missions. Engineers who know the systems of Voyager 1 and Voyager 2 with a depth of familiarity that comes only from long, loving attention. People who have watched the power levels decline year by year, who have made the careful decisions about which instruments to keep and which to sacrifice, who have nursed the aging spacecraft through unexpected challenges with the resourcefulness born of necessity. These people know that the end is coming. They have known it for a long time. They have been planning for it, managing toward it, trying to extract every last piece of scientific value from the dwindling power supply before it finally runs too low. And when the last signal comes, when the final data packet makes its 20-plus hour journey from interstellar space to a dish antenna in California or Spain or Australia, and is received and processed and understood, there will be people in that room who have spent more of their working lives with these spacecraft than without them. What that moment will feel like, we can only imagine. Grief, perhaps. A particular kind of grief that has no simple name. The grief of losing something that was never alive in the biological sense, but that was, in every meaningful human sense, present. Familiar. Known. A companion across decades of work and discovery, and the slow accumulation of understanding. But also, surely, pride. The deepest, most settled kind of pride. The pride of knowing that a thing was done well, that it lasted far longer than anyone had a right to expect, that it did not merely survive, but continued to contribute, continued to discover, continued to matter right up until the very end. After the silence falls, the spacecraft will continue. This is worth dwelling on. The end of communication is not the end of the journey. It is not even close to the end of the journey. Voyager 1 and Voyager 2, after their transmitters have fallen silent and their instruments have gone dark, will still be moving through interstellar space at the same extraordinary speeds they carry today. They will still be following the trajectories that were set in motion by those careful calculations in the early 1970s. They will still be carrying their golden records, their cameras, their now silent instruments, the plaques and the copper discs, and the encoded images of human life. They will drift through the interstellar medium for millions of years, long after the tracking stations that listened for their signals have themselves become dust. Long after the languages spoken by the people who built them have been forgotten or transformed beyond recognition. Long after the civilization that launched them has changed in ways we cannot begin to predict. The universe will keep them. Moving, patient, silent, enduring. There is something in this that speaks, I think, to something very deep about the nature of making things. About the particular human impulse to send something outward, a message, a probe, a work of art, into a future you cannot see, toward a recipient you cannot know, across a distance that makes return impossible. We do this because we believe, in some fundamental way, that the reaching matters, that the attempt is its own justification, that even if no one ever finds the golden record, even if the Voyager spacecraft drift through interstellar space for millions of years without ever being encountered by another intelligence, the fact that they exist, the fact that they were made and launched and listened to for half a century, is itself something, is itself a statement about what we are and what we value and what we think is worth doing. Carl Sagan, who understood this better than almost anyone, wrote that the Voyager spacecraft would outlast the Earth itself, that when the Sun eventually expands in its old age and swallows the inner planets, the Voyager spacecraft will still be out there, drifting through the Milky Way, carrying their records of a world that once existed and a species that once looked up at the stars and wondered and reached. As you breathe here in the quiet, slowly, easily, Without effort, let the bittersweet quality of this settle into you like warmth. The signal is still coming. Tonight, right now, the transmitters on both Voyager spacecraft are still broadcasting. The Deep Space Network is still listening. The data is still flowing, slowly and steadily, across the distance that grows by another 1,000,000 kilometers every day. The candles are still burning. And what they have illuminated, what they have revealed about the solar system and the heliosphere and the interstellar medium and the extraordinary capacity of human ingenuity and patience, will not go dark when they do. The knowledge they have given us is permanent. The maps they have begun to draw of the space between the stars will be completed, eventually, by other missions that follow in their wake. They showed us the way, and when their voices finally fall silent, the silence will not be empty. It will be full of everything they found, everything they measured, everything they sent home across the impossible distance. Full of 50 years of whispers from the dark. Let your eyes grow heavy now. Let the thought of those two small machines, still moving, still transmitting, still faithful to the work they were made to do, settle into the quiet space behind your chest where gratitude lives. They are still out there, still going. And tonight, at least, they are still speaking. Close your eyes for a moment, or let them stay closed, if they already are, and try to hold a number in your mind. 40,000. 40,000 years. It is not a number that the human mind is built to feel. We are creatures of days and seasons, of lifetimes that stretch perhaps a century if we are fortunate, of histories that we struggle to hold clearly beyond a few thousand years. 40,000 years ago, our ancestors were painting animals on the walls of caves in what is now France and Spain. The Lascaux Caves, the Chauvet Cave, with a skill and beauty that still astonishes us when we stand before those images today. Agriculture had not yet been invented. Cities did not exist. The great river civilizations of Egypt and Mesopotamia lay more than 30,000 years in the future. 40,000 years is longer than all of recorded human history several times over. And in approximately 40,000 years from now, Voyager 1 will make its closest approach to another star. Let that land for a moment before we go further. Let the full, quiet weight of it settle. The spacecraft that launched in 1977, built by human hands, assembled in a clean room in California, launched on a summer morning by people who are now elderly or gone, will still be moving through interstellar space in 40,000 years. Long after every record of its launch has been lost. Long after the languages in which its story is told have changed beyond recognition or vanished entirely. Long after the civilization that made it has transformed into something we could not begin to predict. It will still be moving, still following the trajectory set in motion by those careful calculations, by the gravity assists of Jupiter and Saturn, by the fundamental physics of inertial motion in the absence of friction. There is nothing to slow it. There is almost nothing in the space it travels to exert any meaningful force upon it. And so it will drift, patient, silent, enduring, for timescales that dwarf the entirety of human civilization. After the transmitters fall silent, sometime in the 2030s, the Voyager spacecraft will enter a new phase of their existence. No longer explorers sending data home. No longer in conversation with the world that made them. Just objects in motion. Pure inertial drift, as the physicists call it, the simple continuation of movement that began at launch and will continue until something stops it. In the emptiness of interstellar space, almost nothing will stop it. Newton's first law of motion, one of the most fundamental principles in physics, states that an object in motion will remain in motion at the same speed and in the same direction unless acted upon by an external force. In everyday life on Earth, we rarely see this law operating cleanly, because friction and air resistance and gravity are always present, always slowing things down, always redirecting motion. But in interstellar space, those forces are absent or negligibly small. The interstellar medium exerts a tiny drag, almost immeasurably small at the scales involved. The gravity of distant stars tugs, gently, but not enough to significantly alter the trajectory over timescales of tens of thousands of years. And so the Voyager spacecraft will drift. at 17 kilometers per second for Voyager 1, at 15.5 for Voyager 2. The same speeds they travel tonight. The same speeds they have been traveling since the last planetary gravity assist concluded, and the solar system fell behind them. Steady, unchanging, crossing the dark at a rate that seems extraordinary by human standards and glacial by cosmic ones. In approximately 40,000 years, Voyager 1 will make its closest approach to a star called Gliese 445. Gliese 445 is not a star you would know by name. It does not appear in myths or navigational traditions. It has no common name beyond its catalogue designation. It is a small, dim, reddish star, a type known as an M-type dwarf, or red dwarf, located currently about 17.6 light-years from Earth in the constellation Camelopardalis, the giraffe. Red dwarfs are the most common type of star in the Milky Way, making up perhaps 3/4 of all stars in the galaxy. They are smaller, cooler, and far less luminous than our Sun, burning their fuel so slowly that they can remain on the main sequence for hundreds of billions of years, far longer than the current age of the universe. Gliese 445 is itself moving through the galaxy, as all stars do, and its motion is carrying it toward our solar system. In 40,000 years, as Voyager 1 drifts outward and Gliese 445 drifts inward, they will pass one another at a closest distance of approximately 1.6 light-years. 1.6 light-years. To feel the scale of that, remember that a light-year is approximately 9.46 trillion kilometers. 1.6 light-years is therefore roughly 15 trillion kilometers. Voyager 1, traveling at 17 kilometers per second, would need tens of thousands of additional years just to cover that remaining distance. By any human standard, 1.6 light-years is an incomprehensible distance. By galactic standards, the standards of a galaxy roughly 100,000 light-years across, containing hundreds of billions of stars, it is a near miss, a close encounter, a passage through what astronomers would describe as the same neighborhood. The closest approach will not be close enough to matter, physically. The gravity of Gliese 445 will tug at Voyager 1 as it passes, gently reshaping the trajectory by a small degree, but not capturing it, not pulling it into orbit, not significantly altering the path it would otherwise follow. Voyager 1 will drift past, at distances that would take tens of thousands more years to cross, and continue outward into the deeper galaxy beyond. There will be no collision, no dramatic event, no moment of arrival, just a passage, a slow, silent drift through the gravitational neighborhood of a small red star, observed by no one, recorded by no instrument, leaving no trace other than the infinitesimal reshaping of a trajectory by a force too small to meaningfully describe. And then onward, into the dark beyond. While Voyager 1 is making its quiet passage near Gliese 445, its twin will be having its own encounter on the other side of the sky. In approximately the same time frame, around 40,000 years from now, Voyager 2 will pass near a star called Ross 248. This is another red dwarf, small and dim, currently located about 10.3 light-years from Earth in the constellation Andromeda. Like Gliese 445, Ross 248 is in motion through the galaxy, and that motion will bring it closer to our solar system in the coming millennia before it drifts away again. Voyager 2's closest approach to Ross 248 will be approximately 1.7 light-years, slightly further than Voyager 1's pass by Gliese 445, but comparable in scale. A close encounter by galactic standards. A vast, uncrossable distance by any human measure. Again, no collision, no capture, no drama, just a passage through the extended gravitational neighborhood of a star, a gentle reshaping of the trajectory, and then the continued drift into the unknown. Two spacecraft, launched 16 days apart from the same planet, making their first stellar encounters within the same broad window of deep future time, at comparable distances, near stars of similar type, and doing so in entirely different directions, on opposite sides of the solar system's plane, having diverged on their different paths nearly 50 years ago and never converged again. The symmetry of it is quietly beautiful. Let your breathing deepen as you hold these timescales. There is no need to grasp them firmly. They are too large for firm grasping. Let them be what they are: vast, soft, incomprehensible in their particulars, but somehow available in their general shape. The way the ocean is available even when you cannot see across it. 40,000 years. In 40,000 years, the stars themselves will have moved. The constellations we know: Orion, the Big Dipper, Cassiopeia, all the patterns that human beings have been tracing in the sky for as long as we have been human will have shifted into new configurations, unrecognizable from what they are today. The individual stars that make up those patterns are moving through the galaxy at their own speeds, in their own directions, and over tens of thousands of years the accumulated drift becomes significant. The night sky of 40,000 years from now will look different to any eye that might observe it. And in that changed sky, two small spacecraft will be drifting not toward the constellations we know, because those will have shifted, but toward specific coordinates in the galaxy that we can calculate now and trust will be accurate, because orbital mechanics is patient and precise, and the universe honors its own mathematics. There is another detail worth dwelling on as the night deepens around you. Voyager 2, on its path below the plane of the solar system, is expected to spend tens of thousands of years moving through regions of the interstellar medium that are denser and more varied than the relatively thin environment near our solar system. The galaxy is not uniform. The interstellar medium is not evenly distributed. It exists in clouds, some thin and hot, some denser and cooler, some threaded with stronger magnetic fields, some with weaker ones, some enriched with the material of ancient stellar explosions, some representing the more undisturbed primordial distribution of gas and dust. Voyager 2 will drift through these clouds. Not quickly, not dramatically, but steadily, over timescales measured in tens of thousands of years. Each cloud a different environment, a different composition, a different magnetic character. If Voyager 2's instruments were still working, if there were any power left to run them, any transmitter left to send the data home, the measurements from those cloud passages would be extraordinary. A record of the varying texture of the interstellar medium, gathered across thousands of light-years of travel. But there will be no instruments, no power, no signal. The spacecraft will drift through those clouds in complete silence, measuring nothing, telling no one, leaving no record beyond the infinitesimal physical interactions of a small metal object with a thin scattering of gas and dust. The universe will know it happened. We will not. There is something in that, something in the idea of things happening without being witnessed, events occurring in the deep future with no observer to record them, that might feel melancholy on first encounter. But let it soften as you breathe, and see if something else is available underneath the melancholy. The Voyager spacecraft do not need to be witnessed to matter. They do not need to be tracked or measured or communicated with to be real. Their existence, their continuous, patient, unhurried existence across timescales that dwarf all of human history, is complete in itself. The fact that no human will observe Voyager 1's passage near Gliese 445 does not make the passage less real. The universe will be there. The star will be there. The spacecraft will be there. The gravitational interaction will occur exactly as the mathematics predicts, with perfect fidelity to the laws of physics, whether or not any mind is present to appreciate it. There is something quietly liberating about that. About the idea that things can matter without being watched. That the universe does not require an audience for its most extraordinary performances. Voyager 1 will pass near Gliese 445 in 40,000 years, in silence, in the dark, with no one watching. And it will be magnificent. As sleep draws closer now, as the boundary between waking and dreaming grows softer and easier to cross, let the deep future settle around you like a blanket. You are here, in this moment, in this body, on this night. The Voyager spacecraft are out there, moving. In 40,000 years, their paths will carry them near stars that right now are just catalog entries, just numbers in an astronomical database, just small red points of light in telescopes pointed at the sky. But between now and then, in all that vast, unhurried 40,000-year interval, the universe will simply continue. Stars will drift. Galaxies will rotate their slow rotations. The interstellar medium will shift and thin and thicken in its ancient patterns. And two small spacecraft, carrying golden records and the accumulated ambition and curiosity of a species that looked up at the stars and wondered, will drift through all of it. Patient, silent, enduring. The night is deep around you now, and the stars beyond the roof above your head are exactly where they have always been, and somewhere out past all of them, past the last planet, past the heliopause, past everything. The Voyagers are moving through the dark. Let your body be heavy. Let your mind be still. 40,000 years is a long time. You have all night. There is a question that arises, quietly, when you spend time thinking about deep time. Not a frightening question. Not an urgent one. Just a soft, open question that arrives in the stillness between thoughts. The way certain questions only come when the mind has grown quiet enough to receive them. The question is this: what lasts? Not what we want to last. Not what we build with the intention of lasting. But what actually endures. What persists through the indifferent passage of geological and astronomical time, outlasting the intentions and the memories and the very civilizations that brought it into being. It is a question that empires have answered one way, and mountains have answered another. That language is answered differently than mathematics. That music answers differently than stone. And it is a question that the Voyager spacecraft answer, in a way, that is unlike almost anything else our species has ever made. Because the Voyager spacecraft will last longer than almost everything. Let your body grow heavy as you breathe. Let the mattress or the cushion or the surface beneath you take the full weight of everything. You do not need to hold yourself up tonight. You do not need to hold anything. Just breathe, and let the story of deep time wash over you slowly, the way water washes over stone. Without urgency, without force, just the patient, continuous presence of something vast and unhurried. We have followed the Voyager spacecraft from their launch in 1977 to their planetary encounters, through the heliosphere and across the heliopause, into interstellar space, and forward 40,000 years to their quiet passages near distant red stars. Now we go further still. Much further. After those stellar encounters. After Voyager 1 drifts past Gliese 445 and Voyager 2 drifts past Ross 248, in that unimaginable 40,000-year future, the journeys do not end. They simply continue. There is nothing to stop them. There is no wall at the edge of the galaxy, no boundary marker, no gravitational barrier that would catch these small machines and hold them. They will drift onward, through the interstellar medium, through the slow, changing texture of the galaxy's gas and dust. Past stars they will never be close enough to visit, near stellar systems that may or may not harbor planets, through regions of the Milky Way that no human instrument has ever observed at close range, and none ever will. The Milky Way is not a static object. It is a vast, slowly rotating spiral galaxy, a disk of stars and gas and dust roughly 100,000 light-years across, containing somewhere between 100 and 400 billion stars, turning around a central hub that contains a supermassive black hole, 4 million times the mass of our Sun. Everything in the galaxy orbits that center. Our Sun orbits it, carrying the Earth and all the planets with it, at a speed of about 220 kilometers per second, on a roughly circular path that takes approximately 225 million years to complete. One orbit around the Milky Way. 225 million years. In the entire history of complex animal life on Earth, roughly 540 million years, from the Cambrian explosion to the present, the Sun has completed barely 2.5 of those orbits. The dinosaurs lived and died within less than one. The entirety of human existence, from our earliest ancestors to the present moment, occupies a sliver of time, so thin it would not be visible on any diagram drawn to scale. The Voyager spacecraft will orbit the galaxy too. Not on exactly the same path as the Sun. Their trajectories carry them at different angles, different speeds, different directions through the galactic disk, but they are, nonetheless, subject to the gravity of the galaxy as a whole. And that gravity will shape their paths into long, sweeping orbits around the galactic center, carrying them through the Milky Way on timescales measured in hundreds of millions of years. Let that image form slowly behind your closed eyes. The Milky Way as seen from above that vast, luminous spiral, its arms trailing in graceful curves around the bright central hub. And somewhere within it, two tiny specks of metal moving. Too small to see. Too distant to track. Too far from any transmitter for any signal to reach them or leave them. Just drifting, as the galaxy turns its slow, magnificent turn around them. In 225 million years, the Voyager spacecraft will have completed something like one orbit of the Milky Way. The stars around them will be different stars, not just different positions of the same stars, but genuinely different, because stars are born and live and die on timescales of millions to billions of years, and the galaxy will have changed. New stars will have formed in regions that are now cold and dark. Old stars will have exhausted their fuel and collapsed or exploded. The spiral arms will have turned. The galactic center will have continued its slow consumption of infalling material. And Voyager 1 and Voyager 2 will still be there. Silent, dark drifting. Their instruments long since cold and dead. Their transmitters silent for hundreds of millions of years. Their plutonium generators reduced to the elemental products of complete decay. But the structures themselves, the aluminium frames, the titanium components, the gold-plated copper of the records persisting in the cold and airless dark of interstellar space, where there is nothing to corrode them, nothing to erode them, nothing to break them down. The universe, it turns out, is a remarkably good place to store things. The golden records will still be there. This is worth saying slowly, and letting it settle. The golden records those 12-inch discs of gold-plated copper, chosen for their resistance to corrosion, fitted into their aluminium protective covers, engraved with diagrams explaining how to play them, and what they contain are, in practical terms, nearly indestructible in the environment of interstellar space. On Earth, records decay. Materials corrode. Paper yellows and crumbles. Stone erodes under wind and water. Even the most durable of our monuments, the pyramids, the carved faces in granite mountains, will eventually be worn away by geological forces and the patient work of time. The Earth itself will be consumed when the Sun expands into a red giant in approximately 5 billion years, swallowing the inner planets and ending whatever remains of the physical record of human existence on this world. But the Voyager spacecraft will be somewhere else by then. Far from the Sun, far from the expanding shell of the dying star, drifting through the interstellar medium on trajectories that will carry them safely through the death of the solar system and beyond. The golden records will outlast the Earth. Think about what is on those records. The music of Bach, the Brandenburg concertos, intricate and mathematical and achingly beautiful. Chuck Berry's Johnny B. Good, chosen because Carl Sagan wanted to include rock and roll and was told by colleagues that this was undignified, and included it anyway. A Javanese gamelan piece. A Navajo night chant. Georgian choral music. Music from Senegal and Peru and Bulgaria and Japan and Azerbaijan. 55 spoken greetings in 55 languages, including a greeting in ancient Akkadian, a language already dead when the Roman Empire was young. The sound of the wind. Of rain. Of surf. Of thunder. The call of a humpback whale, rising and falling in the dark water of an ocean that will not exist in 5 billion years. The cry of a newborn baby. All of it encoded on gold-plated copper, drifting through the interstellar medium, carried by 2 small spacecraft through the slow turning of the galaxy. There is a word that gets used in discussions of the Voyager golden records, the word message. We say the records are a message from Earth, a message to the cosmos, a message in a bottle cast into the ocean of interstellar space. But there is another way to think about them that feels, in the quiet of this late hour, even more true. They are not only a message, they are a memory of a world that was alive, that had weather and music and languages and whales and newborn babies, preserved in a form that will outlast the world itself. They are the most durable memory our species has ever made. Not durable in the way a hard drive is durable, or a carved inscription, or a printed book, all of which will be destroyed along with the Earth when the Sun expands. Durable in the way that only objects in interstellar space can be durable, removed from all the forces that erode and consume and transform, preserved in the cold and the dark and the emptiness for as long as the galaxy turns. In that sense, the Voyager spacecraft are not just messengers. They are keepers. Quiet, patient, silver keepers of the memory of a living world, carrying that memory outward through time and space long after the world itself is gone. Humanity's first direct messengers to the stars. That phrase, that designation, belongs to Voyager 1 and Voyager 2 alone. No other object has crossed the heliopause. No other human-made thing has entered interstellar space. Every satellite, every space station, every probe that has been launched throughout the history of the space age is still within the heliosphere, or has fallen back to Earth, or has been deliberately directed to impact a planet or moon. Only the two Voyagers have crossed the threshold. Only the two Voyagers are, right now, in the space between the stars. And only the two Voyagers will carry the physical record of human existence out into the galaxy, past the death of the Sun, through the long, slow orbits of deep cosmic time, into a future that we cannot see and cannot reach, but can, in this quiet moment, briefly imagine. There is a particular feeling that arises when you truly let the scale of this settle into you. Not overwhelm, not the vertiginous panic that can come from confronting cosmic scale, too directly, too suddenly, but something gentler, a kind of perspective that arrives softly, like a change in the light. The feeling that the universe is very large, and very old, and very patient. That within it, human beings are very small, and very young, and very brief. And that in spite of all of that, or perhaps because of all of that, two people on an ordinary day in 1977 were part of a team that launched two spacecraft that are now in interstellar space, carrying gold records of music and voices and whale song, destined to orbit the Milky Way for hundreds of millions of years and outlast the Earth itself. Small and brief, and yet capable of that. There is no contradiction in holding both things at once. The smallness and the reaching, the brevity and the endurance, the uncertainty and the mathematical precision of an orbital trajectory calculated 50 years ago that is still correct today and will still be correct in 40,000 years. We are small. What we made is not. The night is very deep now. Your breathing has slowed to something easy and natural, the rhythm of a body that is ready for rest, that has been ready for a while and has simply been waiting for the mind to catch up. The thoughts that were sharp earlier in the evening have softened into something more like images. Loose, drifting, not quite real and not quite gone. Let the Voyager spacecraft drift with them. Let Voyager 1 sail above the plane of the galaxy, toward Ophiuchus and beyond, through the slow turning of the Milky Way, past the death of the Sun, through the orbits of deep time, carrying its golden record into the unimaginable future. Let Voyager 2 drift below, toward Telescopium, through the interstellar clouds, past Ross 248, onward into the same vast dark, carrying its own golden record, its own cargo of music and voices, and the sounds of a world that loved the light. They are not lost. They know exactly where they are going, in the sense that physics knows. Their trajectories are precise, their paths calculable, their futures as certain as the laws of motion that govern everything in this universe. They are not alone, in the sense that they carry with them the best of what we made and loved and wanted to share. And they are not ending. They are simply continuing. As the universe continues, as the galaxy continues, as the slow and patient work of time continues, without urgency, without destination, without the need for any particular thing to happen next. Just the drift, just the dark, just the golden record, turning slowly in the interstellar cold, carrying the sound of rain, and the call of a whale, and the cry of a newborn baby out into the silence between the stars. Close your eyes. You have traveled very far tonight. Rest now. The Voyagers will carry the rest of the journey for you. There is a moment, in the very deepest part of a quiet night, when the world seems to pause. Not stop. Never stop, because the world does not stop, the earth does not stop its turning, the stars do not stop their slow drift across the sky, the galaxy does not pause its ancient rotation, even for a breath. But there is a quality that arrives in the deepest hours, a stillness that settles over everything, a hush that feels less like the absence of sound, and more like the presence of something very large and very patient that has always been there, and is only now, in the quiet, perceptible. You may be feeling something like that now. The heaviness of a body that has been still for a long time. The looseness of a mind that has let go of its grip on the day. The particular quality of darkness behind closed eyes that is different from the darkness of a room. Softer, deeper, threaded with the faint phosphorescent drift of a mind beginning to dream. This is where we end our journey tonight. Not with a launch, not with a crossing, not with the data of instruments measuring the interstellar medium. But here, in this stillness, in this moment that is both very small, one person, one night, one quiet room, and in its own way, connected to something almost incomprehensibly large. Think, for the last time tonight, about what was made. In the early 1970s, a group of engineers and scientists at a laboratory in Pasadena, California, began building 2 spacecraft. They worked with the tools available to them, slide rules and early computers, hand-drawn circuit diagrams and machined metal components, the accumulated knowledge of a space program that was barely 15 years old. They worked carefully because they understood that what they were building would have to survive for a very long time in a very unforgiving environment. They built the spacecraft to last perhaps 5 years. Perhaps a little more, if things went well. Things went extraordinarily well. What they built has now been traveling for nearly 50 years. It has crossed the entire span of the planetary solar system. It has flown past worlds that were once only smudges of light in telescopes and transformed them into known places. Jupiter with its volcanic moons and its ancient storm, Saturn with its impossibly thin and impossibly beautiful rings, Uranus tilted on its side, Neptune roaring with the fastest winds in the solar system. It has crossed the termination shock, where the solar wind slows. It has traversed the heliosheath, that turbulent outer layer of the Sun's extended atmosphere. It has crossed the heliopause, the true edge of the solar system, the boundary where the Sun's breath ends and the breath of the galaxy begins, and it has entered interstellar space. It is there now. Both of them are there now, tonight, as you lie here in the quiet. And they are carrying something. This is the detail that stays with you, the one that sits differently from all the other extraordinary facts of the Voyager story. The orbital mechanics, the gravity assists, the instrument packages, the power systems, all of these are remarkable, all of them deserve the wonder they inspire. But the golden records are something else. The golden records were not necessary for the mission. They did not help the spacecraft navigate, or measure the magnetic field, or count the cosmic rays arriving from outside the heliosphere. They added weight, a small amount, but weight nonetheless, to spacecraft where every gram had to be justified. They required time and resources, and the attention of some of the most creative minds involved in the mission. And the chances of them ever being found, ever being played, ever being heard by any intelligence other than the one that made them, those chances are, in any realistic assessment, vanishingly small. They were made anyway. Carl Sagan, who led the Golden Record project, understood something important about why. It was not, primarily, about the probability of contact. It was about the act of reaching, about the statement that the reaching itself makes, about who we are, and what we value, and what we think is worth sending out into the universe, even in the almost certain knowledge that it will travel forever in silence. We sent music. We sent greetings in 55 languages. We sent the sound of the wind, and the rain, and the surf. We sent the call of the humpback whale, and the cry of a newborn baby. We sent mathematical diagrams and encoded photographs of a mother nursing her child and a forest at sunrise, and the chemical structure of DNA. We sent all of this into the dark, knowing it would almost certainly never be received, because we are the kind of creature that reaches. Because curiosity and the desire to share what we have found and made and loved are not incidental features of human nature. They are central to it. They are perhaps the best of us. The Voyager spacecraft were built to explore the outer planets. They were built to visit Jupiter and Saturn, to photograph their moons, to measure their magnetic fields, to gather the data that would transform these distant worlds from points of light into understood places. That was the mission. That was what the engineers designed for, what the scientists planned for, what the funding was allocated for. And they accomplished all of it. More than all of it. But somewhere along the way, in the decades of continued operation, after the planetary encounters were complete, in the slow outward journey through the heliosphere, in the crossing of the heliopause and the entry into interstellar space, they became something that no mission plan had anticipated. Something that the engineers who built them to last 5 years could not have imagined when they were assembling them in that clean room in California. They became humanity's first travelers to the stars. Not in the sense of reaching any star. The distances are too vast, the speeds too slow, the timescales too long for anything so dramatic. But in the sense of leaving, of crossing the boundary, of passing beyond the sun's kingdom and entering the space that belongs to the galaxy. The ancient, cold, thinly threaded space that lies between stellar systems and has lain there, largely undisturbed, since long before the sun was born. No human-made object had ever been there before. They are there now, and they will carry the record of what we are into a future measured not in years, but in millions of them. Let that phrase rest in you for a moment, in this quiet, in this darkness, with the weight of sleep already gathering at the edges of your awareness. Millions of years. The golden records on the Voyager spacecraft will outlast every monument humanity has ever built. They will outlast every language we have ever spoken. They will outlast every city, every institution, every civilization that has ever risen or will ever rise on this small planet. They will outlast the Earth itself, drifting safely through interstellar space while the sun expands in its old age and the inner planets are consumed. And what they carry, encoded in the spiral grooves of gold-plated copper, protected by the aluminium covers engraved with instructions for any intelligence that might one day find them, is a memory. A memory of rain and music and the deep song of whales moving through dark water. A memory of a mother and a child. A memory of sunlight and DNA and the mathematical constants that describe the universe we live in. A memory of us, of what we were on one small planet, in one brief and extraordinary chapter of cosmic time, when we looked up at the stars and felt, simultaneously, the full weight of our smallness and the full reach of our curiosity. Both things at once. Always both things at once. The night is at its deepest now. Outside, the stars are where they have always been, Ophiuchus climbing somewhere above the horizon, Telescopium somewhere below it in the southern sky, and somewhere beyond both, so far beyond that the distance has ceased to be a number and become simply a quality of the dark, 2 small spacecraft moving through the silence. They are not waiting to arrive anywhere. They have no destination. They are simply going, steadily, patiently, faithfully, in the direction that physics and the gravity of long-ago planetary encounters set for them nearly 50 years ago. The trajectory is clean and true. The mathematics will hold for as long as the galaxy holds. There is nothing to stop them, and so they will not stop. They will pass near Gliese 445 in 40,000 years, in silence, in the dark. They will complete one orbit of the Milky Way in 225 million years, carrying their golden records through the slow turning of the galaxy. They will still be drifting when the sun is gone, when the Earth is gone, when everything that we have ever built or said or sung has long since been returned to the atoms from which it came. And on the side of each spacecraft, a golden record will still be there, waiting in the way that only truly patient things can wait, without awareness, without hope, without expectation, just present, just there, just carrying, in its spiral grooves, the sound of rain on a world that loved the light. You have traveled very far tonight. From a launch pad in Florida in the summer of 1977 to the edge of interstellar space and beyond, through 40,000 years and 225 million more, through the deep future of the galaxy and the long, slow orbit of everything around the bright heart of the Milky Way. You can rest now. The spacecraft are still moving. The records are still there. The mathematics is still true, and the trajectory is still clean. And somewhere in the dark between the stars, Two small golden messengers are sailing outward through a silence more complete and more ancient than anything our minds were built to hold. They were built to explore the outer planets. Instead, they became something far greater. Humanity's first travelers to the stars, carrying a small record of Earth into a future measured not in years, but in millions of them. Let your eyes stay closed. Let your breathing be easy and slow. Let the stars turn overhead in their patient way, and let the galaxy turn beneath them in its slower way, and let the Voyagers sail on through all of it. Through the dark, through the silence, through the unimaginable reaches of time. While you rest here, warm and still, on the small and beautiful world that made them. Good night.